All right. So let's look at an important theorem in the study of prime numbers. This theorem is that there are infinitely many prime numbers. So that list of primes is never going to come to an end. You can keep going forever with primes. Now, the proof I'm going to show you for this is, I believe, attributed to Euclid, who Euclid, you may remember, was a Greek fellow who sort of pioneered geometry, at least in some sense. I'm sure there was lots of geometry done before Euclid, but a lot of what we think of as like classical geometry is what Euclid wrote about. Euclid's Elements is a book on geometry that you may have heard of before. So that's the Euclid we're talking about here. So the proof of this is by contradiction. Oopsie. Okay, so it goes like this. Suppose there are instead finitely many primes. If there are, then we can list them. P1, P2, P3, and so on. And there's going to be a last prime number. We'll call it Pn. So in this case, little n is the number of prime numbers we have. So we're assuming it's finite. We're assuming that this list stops. Okay. Now what we're going to do is we're going to look at another number, a specific number. So consider this number. We're going to call it q, and we're going to calculate it by taking all those prime numbers that we have and multiplying them together. So p1 times p2 times ... times pn. Okay, multiply those up and then add 1. First of all, it should be noted that q is not equal to pi for all I in this set from 1 to n. And the reason it's not equal to any of those primes is that it's bigger than them, right? It's multiply them all together and then add 1. It's clearly going to be larger than any of those prime numbers individually. Remember that prime numbers are specifically positive integers, right? Greater than 1. So these are you're never going to get like a negative number and then add 1. So this is definitely going to be bigger, therefore not equal. That means that if we're assuming that these are the only prime numbers, q in this case must be composite, right? So q must be composite, which means q is going to have a prime divisor, right? So there exists an I in this set here from 1 to n, such that pi, that prime number, divides q. Okay, if it's composite, it must have a prime divisor. So pi divides q. But let's see what happens if pi divides q. Well, first of all, that means q can be written as pi times k for some, integer k. That's what it means to be a divisor. So q is a multiple of this pi, with the multiple being k. And then we can write, it's time for a little bit of algebra. We can write pi times k equals p1 times p2 times ... times pn, and then plus 1. Now I'm going to subtract this product of prime numbers from both sides. So we get pi times k minus p1 times p2 times ... times pn. And that is going to equal 1. Sorry, I ignore that scribble. I started writing the wrong symbol. Now here's the problem with this, right? Remember, this is proof by contradiction. So we should be, since I told you that, you should now be expecting there to be some kind of contradiction which we encounter. Here's the problem. Pi is a factor of this first term, and pi is going to be somewhere in here, okay, somewhere in this product of primes. So what we're going to be able to do is say that pi can be factored out of this, and what remains is going to be an integer, right? Pi is a factor of both these terms, and therefore a factor of this entire thing. So this means pi divides 1. But if pi is a prime number that divides 1, that doesn't even make any sense. That in itself is a contradiction. There cannot exist a prime number that divides 1. The only number that divides 1 is 1 itself, and 1 is not prime by definition. So we can't have a prime number dividing 1. That's a contradiction. So that was great. So we ended up showing that this is in fact impossible. We can't have a finite number of primes, and therefore we must have an infinite number of primes. By the way, this theorem is, or the proof of this theorem rather, is non-constructive, right? Like we didn't actually find another prime number. If you take a bunch of primes and multiply them together and then add 1, we didn't actually show that that is guaranteed to be a prime, right? Q might not actually be a prime. You can take prime numbers and multiply them and then add 1 and end up with something which is not prime. In fact, that's super easy to do if you take all of these numbers. If you take only like odd prime numbers, like 3 and 5 and 7, multiply them together, you're still going to have an odd number. Add 1 and you're going to have an even number, which is not going to be prime, right? So we didn't actually say that Q is going to be a prime number. We just said that if you do this, then you're going to get a contradiction. So it's non-constructive, right? This is by no means a formula for generating primes. That's not what we found, right? Just a proof that there will be an infinite number of primes. Okay, so now that we know that there's an infinite number of primes, it turns out finding large prime numbers is useful. As I mentioned, I think before I started the lesson, there's sort of a search for large prime numbers. It's ongoing search for larger and larger prime numbers, and there are people across the world dedicating their computer processors to algorithms that are searching for larger prime numbers. And sometimes people find a new large prime number and have a little party to celebrate the discovery of the new largest prime number ever discovered. I want to introduce a certain type of prime number called a Mercen prime. So Mercen primes, all of the largest known prime numbers are of this special type called Mercen primes. And they are prime numbers that are of the form 2 to the power p minus 1, where p is prime. It turns out that if you do 2 to the power n minus 1, then if n is not a prime number, so if that exponent there is not a prime, if it's composite, it turns out that the result is guaranteed not to be composite as well. And there's an exercise in the book where you prove that. I think I might have assigned it for the homework. So if this is going to be a prime number, it has to be a prime power up there, but it's not a guarantee. So this is not necessarily prime. There are prime numbers that are one less than a power of 2, but not all of them, so not necessarily prime. However, it is easy to test whether a 2 to the p minus 1 is prime or not. There's a thing called the Lucas-Lehmer test. L, it's supposed to be an L. The Lucas-Lehmer test, which is I don't actually know how it works, but that is the name of the test that they can apply to a number like this, just to check to see whether it's prime or not. And apparently that test can be done relatively easily. So that's why the largest known prime numbers are these Mercen primes. They certainly don't constitute all prime numbers. Like most prime numbers are not Mercen primes. But they certainly are the easiest ones to find, and therefore the biggest ones are of this type. So if you're interested in searching for prime numbers, you can. I should have looked up before making the video. I should have looked it up. But ask me if you're interested, because you can actually dedicate some of your processor time. Like you can dedicate your computer while it's not doing anything for you. You can have it helping people search for prime numbers, and it's kind of fun to have your computer contributing to something like that when you're not using it. Similarly, you can have you dedicate your computer to helping find more digits of pi, which is another kind of fun little pursuit that we do in mathematics. So that's all I wanted to say about that.